Problem of the day 3. Problems of the day. So I told you this was an Sn1 reaction. So if you hear an Sn1 reaction, what do you immediately think of? More than one step. First step is a leaving group leaves, which means you go through a carbocation, which means you are prone to rearrangements. Now, in this one, if you just even look at the product, you probably already noticed, well, wait a second, like, looks like this is moved, right? There probably was some sort of rearrangement already, right? Hopefully you recognize that. Also notice there's no more wedges and hatches because you're going to make a carbocation, so you're going to lose that. So what happens first? Leaving group leaves. At this point we can do a resonance. Resonance arrow. So why would we do this resonance? We went from secondary allylic to tertiary allylic. This is more stable. So now what reacts? The solvent, just because there's more of it. Also, that's what's in the final thing. Solvent reacts. Don't lose a hydrogen. Don't lose any carbons from your solvent. The final step then for these is going to be a deprotonation. Deprot. And that gets us to our final product. We don't need to worry about wedges and hatches here because did we make an asymmetric center? Nope. Key things, carbocation, leaving group leaves. If you have a carbocation, you can do rearrangements. Secondary allylic versus tertiary allylic. This is more stable. Solvent reacts because there's more of it. Final step, deprotonation. Don't lose any carbons, don't lose any hydrogen until you're supposed to. So acid catalyzed hydration with a protic solvent. First thing that's going to happen, pi bond reacts. We're going to make that carbocation on the more substituted carbon. Secondary carbocation, can we make this more stable? We can by doing a rearrangement. That methyl shift or alkyl shift. Carbon there. Right there. Tertiary went from a secondary carbocation to a tertiary carbocation, more stable. Solvent's going to react now. Our polar protic solvent is the key here. Has to be that protic solvent. Remember NH, OH, pH, or SH in this case. That adds in. The last step here is going to be a deprotonation. The H is just literally going to fall off. The electrons go back to sulfur. Deprot. There you go. Did you make an asymmetric center? No, you didn't. Methyl, sulfur methyl, and then 2 isopropyls. So this is not bonded to 4 different things. So no, there's no new asymmetric center there.